refrigeration system, the refrigerant is air. Okay. So let us see the mechanical refrigeration in that vapor compression refrigeration. So the main difference with air refrigeration and vapor compression refrigeration is that, so here the refrigerant is a substance so which can change its phase. Okay, so it may be converted from liquid to vapor or vapor to liquid. So while converting liquid to vapor, so it will take the heat from the evaporator. So similarly, while giving out heat in the condenser, so the vapor will be converted into liquid state. So that is the main advantage of vapor compression refrigeration system. So nowadays the system used is mainly vapor compression refrigeration. So which can use it from even low capacity to high capacity systems, even from 0.5 tons to even more than 250 tons capacity we can use vapor compression refrigeration system. So the main four components required for vapor compression refrigeration are compressor, condenser, then an expansion valve and then an evaporator. So you can see the flow diagram. So the first vapor compression system was developed in 1835 by Jntuk Moocs. So you can see the four main components required: compressor, condenser, expansion valve and then the evaporator. So the compressor, main function of the compressor is to increase the pressure of the refrigerant. So when the refrigerant comes into condenser, whatever the heat that is given in form of work input to the compressor is given out in the condenser. So you can see the heat given out is Q. And here then the refrigerant will come out as a liquid at high pressure. So when the refrigerant is expanded through an expansion valve, so here the process is the throttling process. So at control rate, the liquid refrigerant passes into the expansion valve. So no work is done in the throttling process. So here the expansion will be isenthalpic expansion. So from this expansion valve, the refrigerant will be in a liquid state, so which will come out at low pressure. So that can take the heat from the evaporator to be cooled or the space to be refrigerated. So this is the most commonly used refrigeration system in the world. So which can be from very low capacity to even very high capacity. So you can see the ideal vapor compression refrigeration cycle. So the main four processes are compression, condensation, then expansion and then evaporation as a refrigerating effect from the evaporator. So 1 to 2 is compression. In the ideal cycle we can assume that 1 to 2 is isentropic compression. Okay, but in actual case this is not isentropic, so that will be always polytropic. We will see that actual cycle later on. So 1 to 2 is isentropic compression in the compressor. Then 2 to 3. So whatever the heat that is taken away in the evaporator and whatever the heat equivalent of the work given out in the compressor. So both will be given out in the condenser. So in the condenser, condensation takes place at constant pressure. Okay, and here so point 2 is in the superheated condition. So here desuperheating is also taking place and also latent heat rejection also taking place in the condenser. So after condensation, the refrigerant at 3 is in the liquid state at high pressure. So when it is passed through an expansion valve, so throttling takes place. So due to that 3-4 is nothing but here throttling process, that is the expansion which is assumed as isenthalpic expansion. So 4 is the condition of the refrigerant which comes at low pressure and temperature, which can take heat from the chamber to be cooled or from the chamber to be refrigerated. So you can see again the flow diagram with compressor, condenser, expansion valve and the evaporator and all the ideal processes. So the difference between reversed Carnot cycle and this one here is that what are the main differences is, so heat rejection is not completely isenthalpic. Okay, So it is constant pressure heat rejection takes place. So 3-4 is again the expansion is throttling expansion. So the expansion valve use the capillary tube. So the capillary tube is the size and the length itself shows the throttling action in that capillary tube. So this is the most widely used cycle for the refrigerators because the COP of the vapor compression refrigeration is very high. So why it is more is because the refrigerant can change its phase. Okay, so it will convert into liquid and it will convert into vapor. Okay, so during condensation, so the refrigerant will be converted into liquid state, while evaporation it will convert into vapor state. So that's why the quantity of refrigerant required is also less. So the different 4 processes given are again explained in this. So process 1 to 2, vapor refrigerant is compressed to a relatively high temperature and pressure, so requiring some work input. So that work input indicates here. So in the air refrigeration, whatever you have seen is, so during expansion also we can get some work. So that will reduce the total work required in the compressor. But that is not the case in vapor compression system. So no work is done during expansion. So whatever the work input is required is completely given to the compressor itself. Then process 2-3. So the vapor refrigerant condenses to liquid through the medium used. That medium used may be brine solution or even water may also be used. So whatever the heat that is gained in the evaporator, the space to be cooled or the space to be refrigerated, and the heat equivalent of the work given out in the compressor, both will be rejected in the condenser. Then process 3-4. So the liquid refrigerant expands in the expansion valve here to the evaporator pressure. So the maximum pressure is nothing but here the condenser pressure, and the minimum pressure here is the evaporator pressure. So that pressure difference is created due to expansion in the expansion valve. Then process 4-1. So that is the here the refrigerant comes from the expansion valve is in the liquid state. So that can take the heat from the chamber to be cooled, and it can be at the suction of the compressor. It may be in the liquid state, or maybe completely in the dry and saturated state, or sometimes it may be even in the superheated state also. Okay. So compression can be divided into 2 types. One is wet compression, then the other is dry compression. Okay. So 1 to 2 is nothing but the compression process which we have assumed is isentropic compression. So if the whole process is done in the wet state, so that is it is not coming in the vapor state, then that compression is called as wet compression. So at the inlet of the compressor, if that is dry and saturated or superheated state, and the compression is taking place completely in the superheated state, then that is called as the dry compression. So the 4 components is the compressor, condenser, expansion valve, and the evaporator. So in the compressor, the low pressure refrigerant is compressed in the compressor to a high pressure and high temperature vapor. So here the refrigerant is in the vapor state at the end of the compression. So at the suction of the compression, it may be in the wet state, or maybe in the dry state, or maybe in the superheated state also. Okay. But the end of the compression, again it may be in the wet state or maybe in the superheated state. So we'll see that also. What are the advantages of dry compression and what are the disadvantages of wet compression? Then condenser. So condenser is nothing but a cooler, so which consists of number of coils through which water is used, or otherwise sometimes brine solution is also used for taking the heat, okay, from the refrigerant which is in the vapor state. And in the condenser, so here the refrigerant will be converted into the liquid. So it will be assumed as the refrigerant is coming out of the condenser in the liquid state, saturated liquid condition. Then in the expansion valve, so it acts as a throttle valve, so where throttling is taking place from low high pressure to low pressure. So the required temperature in the evaporator can be maintained by this torque expansion valve itself. By adjusting this valve, we can maintain the required temperature in the evaporator. Maybe 0 degrees centigrade or less than that. So that can be maintained in the evaporator by adjusting the throttle valve. Then evaporator. So evaporator is nothing but again a heat exchanger. Okay. So where here the heat is to be removed. So that is here also it consists of number of pipes through which the liquid refrigerant coming from the expansion valve passes, and around that there will be brine solution may be there, or air to be cooled, or otherwise water to be cooled, whatever the medium is there. So that will take the heat from the medium to be cooled or to be refrigerated. So this is the diagram showing the two pressures. So the compressor, condenser, expansion valve and the evaporator. So the low pressure side is nothing but, so the evaporator is always in the low pressure side. At the suction of the compressor also the pressure is less. So at the exit of the compressor, so the high pressure is there, and the condenser is also in the high pressure side. So expansion valve function is to reduce the pressure of this by passing through the expansion valve. That may be capillary tube or throttle valve, whatever it is. So the next figure you can see. So that is the diagram showing the temperature versus entropy. So TS diagram. So 1 is at the suction of the compressor. So 1 to 2 is compression. So which is assumed as isentropic compression. And here you can see at the suction of the compressor, the refrigerant is dry and saturated. So the left side line curve is nothing but the liquid line. So right side is the vapor line. Okay. So 1 is dry and saturated state. So 2 will be obviously it will be in the superheated condition. Okay. So during condensation here, so the heat at 2 in the refrigerant is to be removed. Okay. So that removal is taking place in two forms. Okay. So de-superheating. So 2 to, so the vapor line. So that is nothing but de-superheating of the refrigerant, and from the vapor line to 1. So that is nothing but latent heat removal. Okay. Then 1 to 4. So that is the throttling process. So because this is a irreversible process and isenthalpic, it is denoted by the dotted line. So from this, so wet compression means at the suction of the compressor, the refrigerant is in the liquid state. Okay. So it is to the left of the point 1. Okay. Even 2 is nothing but after compression also. So that is in the liquid line only. So that is in between the liquid line. So it is having some dryness fraction. So that may be always less than 1. Okay. So wet compression means, so that 1 to 2 is within the curve only. Okay. So dry compression means, so it should be on the saturated vapor state. At the suction of the compressor, the refrigerant is in the saturated vapor state, and the compression is taking place in the superheated condition. So we have seen already the reversed Carnot cycle. So let us see the comparison between vapor compression cycle and the reversed Carnot cycle. So in the reversed Carnot cycle, whatever we have assumed is all the processes are completely reversible processes. So that's why the COP of the reversed Carnot cycle is also maximum. Okay. So in that for the reversed Carnot refrigeration system, the 4 components required are compressor, condenser, turbine and the evaporator itself. So in this here, so turbine, instead of turbine here, the expansion valve, the capillary tube is used. Okay. So this cycle involves, so in the reversed Carnot cycle involves 2 isothermal heat transfer process and 2 isentropic process. So isentropic compression, isentropic expansion in the compressor and turbine, and heat rejection is again isothermal in the condenser and also in the evaporator. Okay. So refrigerating effect is obtained at the evaporator as the refrigerant undergoes the process of vaporization and extracts the latent heat from the low temperature heat source. You can see the diagram comparing the reversed Carnot cycle with the vapor compression cycle. So here the vapor compression cycle is given by 1, 2, 3, 4, 1. Okay. So that cycle, closed cycle is 1, 2, 3, 4, 1. So that is the vapor compression cycle. So whereas the reversed Carnot cycle is 1, 2, double dash, then 3 dash 1, or otherwise you can also take 1, 2 double dash, 3, 4 dash, and again 1. Okay, that is the rectangle representing smaller rectangle or bigger rectangle representing the reversed Carnot cycle. So whereas the vapor compression cycle is represented by 1, 2, 3, 4, 1. Okay. So both the cycles are operating at the same condenser temperature and the same evaporator temperature. Okay. So the main deviations of vapor compression cycle. The main deviations of the vapor compression cycle from the reversed Carnot cycle. You can see. So that is 2 dash 2 double dash 2. Okay, that is the triangle. So representing. So that is the triangle called as the superheat horn. Okay. So that area is represented by superheat horn. And also the other deviation you can see is, so if you take the reversed Carnot cycle as 1, 2 double dash 3, 4 dash, and 1, 2 double dash 3, 4 is the vapor compression cycle. So the main deviation here is 3, 4, 3, 4, 4 dash 3. So 3, 4, 4 dash 3. Okay. So the lower area. Yes, that one. So that is the other deviation. So that deviation represents the loss in the refrigerating effect. Okay. So the refrigerating effect produced in reversed Carnot cycle is the area under 1, 4 dash. Okay. So whereas in the vapor compression refrigeration cycle, the refrigerating effect is the area under 1, 4. Okay. So due to this here, the refrigerating effect is decreased by, so H4 minus H4 dash. Okay. So that is the loss in the refrigerating effect. And also the work input is also increasing. The work input is increased by the area superheat horn, that is 2 double dash 2 2 dash. So that is the work input is increased and the refrigerating effect is also reduced in the vapor compression refrigeration cycle. So with the effect, the COP also decreases because the refrigerating effect is also reduced and work input is also increased. So again the same diagram I have drawn. So the area 4 dash CD represents a loss of the refrigerating effect. So the area under 3 4. Okay. So you can see the area under 4 dash is nothing but 4 dash CD representing loss of refrigerating effect in the vapor compression cycle. So due to throttling. Then area 4 dash CD. Okay, also represents a loss of positive work resulting from failure of the expansion work. We are not getting any work from the expansion, whereas in the reversed Carnot cycle we are getting some work. Then area 2 dash 2 double dash, that is the superheat horn representing an increase in the work input to the compressor. So that is also the negative work. So more work is required. So with this, the refrigerating effect is reduced and also the work input is also increased in the vapor compression refrigeration system. So with the effect COP of the vapor compression refrigeration cycle is always less than that of the reversed Carnot cycle. So here already we have seen dry compression and wet compression. So always dry compression is preferred rather than wet compression. So due to wet compression always there will be wear and tear on the cylinder head will be taking place. Okay, and also so some amount of moisture will always there in the wet compression. So due to that more work is also required. So dry compression is always presumed. So it is a, if nothing is mentioned in the problem, always you can assume that the compression is at the suction of the compressor. So the vapor refrigerant is taken. So vapor or the refrigerant is dry and saturated. And here the compressor operates. So isentropic compression we are assuming and the throttling process assuming during the expansion. So for the analysis of this, we can find out the COP of the vapor compression refrigeration cycle. So in the evaporator, so what is the heat taken away from the space to be cooled or the space to be refrigerated is H1 minus H4 per kg of the refrigerant. So that is Q in is nothing but the heat taken away in the evaporator or the refrigerating effect produced in the evaporator. So that can be expressed as the refrigeration capacity, which may be in kilowatt per SI unit. And common alternate unit is the ton of refrigeration. As we have seen, ton of refrigeration is nothing but 3.52 kilowatt or otherwise equal to 210 kilojoules per minute. So vapor compression refrigeration cycle can be analyzed if you know the ton of refrigeration and the temperature required in the evaporator and also the atmospheric temperature. If you know all these three, you can find out anything. How much of heat is rejected in the condenser or what is the work input required to the compressor and how much heat is taken away from the evaporator. Next. So also you can find out what is the work required for running the compressor. So per kg of the refrigerant you can take this as H2 minus H1. So because we are assuming that is the isentropic compression process. So 2 is at the delivery of the compressor, 1 is nothing but the enthalpy of the vapor at the suction of the compressor. So with H2 minus H1 you can find out what is the work input to the compressor. Similarly, what is the heat rejected in the condenser? So heat rejected in the condenser is nothing but the heat taken away from the chamber to be cooled, that is the evaporator, and also the work input to the compressor. Both will be rejected in the condenser. So that is nothing but H2 minus H. So where H2 is nothing but the heat of the refrigerant, that is at the discharge of the compressor, and H3 is nothing but so the enthalpy of the refrigerant coming from the condenser, which is in the liquid state. Then expansion. So here expansion is nothing but the throttling process. So here we are assuming that this throttling process is always enthalpy is constant enthalpy process. So at the end of the expansion, whatever the enthalpy available is same as the enthalpy at the beginning of the throttling process. So H4 and H3 are same. So H4 and H3 you can find out from the given diagram also, pH chart or CS diagram. So directly you can take the liquid enthalpy. So 1 to 2 is isentropic compression. So here S2 is equal to S1. So in this case, if S1 is known, so you can equate S2. So from that also you can find out what is the superheating temperature of the refrigerant at 2. Okay. So even 1 may be in the wet state also. So at that also you have to equate S1 with S2. If you know the dryness fraction at 1, we can find out what is the enthalpy at 1. Okay, which is nothing but fluid enthalpy or the liquid enthalpy plus X into latent heat. Okay, HF plus X into HFG or Hg minus HF. So with that you can find out enthalpy at 1 and also enthalpy at 2. And 3 is nothing but here enthalpy at 3 is the liquid enthalpy at the given temperature or otherwise pressure. So H3 is equal to H4. So from that you can find out the COP, that is the ratio of the refrigerating effect to the compressor work. So refrigerating effect is H1 minus H4 per kg of the refrigerant, and the work input to the compressor is again H2 minus H1. Okay. So H2 minus H1. With that you can find out the COP. And the below figure you can see the pH chart, the pH diagram. So you can see the two pressures. So condenser pressure and the evaporator pressure. So which are constant or horizontal lines here. And here, so at the suction of the compressor, the refrigerant is dry and saturated. At the end of the compression, it is superheated state. So 2, 3 is nothing but the condensation, okay, in the condenser, and 3, 4 is the isentropic expansion in the expansion valve. So with that, you can, if at the suction of the compressor the refrigerant is in the wet state, then you have to know the dryness fraction to find out the enthalpy at 1. So similarly at 2 also, if it is in the wet state, there also you have to know the dryness fraction to find out the enthalpy at 2. Okay. So for that you have to equate the entropies. So S1 should be equal to S2. Okay. If one entropy is known, we can find out the dryness fraction at 2. So this is the coefficient of performance for the Vapour compression refrigeration cycle. So the refrigerating effect is produced during the process 4-1. So that is H1 minus H4 by the work input to the compressor. So that is H2 minus H1. So whereas in the reversed Carnot cycle, so the two temperatures are nothing but the condenser temperature and evaporator temperature. So with that we can find out the coefficient of performance for the reversed Carnot cycle. So which is nothing but the lower temperature by the difference between the two temperatures. So that coefficient of performance of the reversed Carnot cycle is always greater than that of Vapour compression refrigeration cycle. So that is the maximum theoretical coefficient of performance of any refrigeration cycle operating between the cold and hot region. So Tc and Th. Those are the temperatures required in the condenser and the evaporator. Then Ewing is one scientist. He told that always the suction of the compressor should be to the right of 4. Okay. So here also 1 to 2 is compression, 2 to 3 then heat rejection in the condenser, and 3, 4 is expansion, and 4, 1 is the refrigerating effect produced in the evaporator. And here in case after expansion, so that is after the throttling process 4, if directly work input is given to increase the pressure. Okay. So at 4 itself, if compression of the refrigerant is taking place, then what will happen? The refrigerating effect produced will be 0. Okay. So to get some refrigerating effect, always the suction of the compressor, so it should be to the right of 4. Okay. So from 4, if it comes to 1, then the refrigerating produced is nothing but H1 minus H4. Okay. Similarly, if 1m is another point at the suction of the compressor. So in that case also, so the refrigerating effect is produced is increased by the area under 1 m, okay, below that area. Okay. So similarly, at the suction of the compressor, so the refrigerant is in 1s. So 1s is the vapor state, dry and saturated vapor state. So in that case, we can get more refrigerating effect. Okay. So according to him, Ewing, so he found that always at the suction of the compressor, when the refrigerant is in the wet state, and at the end of the compression, if it is in the superheated state, then we can get more COP. Okay. So obviously more refrigerating effect also. So 1 m is nothing but at the suction of the compressor, the refrigerant is in the wet state. Then 2 m is the, so 1 m, 2 m is nothing but the isentropic compression process. So at the end of the compression, so that is 2 m, it is in the superheated state. So with that, we can increase the refrigerating effect. So that also increases the work input to the compressor also. Okay. So our main aim is to get more refrigerating effect. Okay. Even the work input to the compressor is also more, but we have to get the required refrigerating effect. So according to him, so the COP will be maximum at the when the refrigerant at the suction of the compressor is in the wet state, and at the end of the compression it is in the superheated state. So COP is 0 at 4. Okay. So COP is 0 at 4. So because here at 4 itself this compression is taking place to 5. Okay. So to get the refrigerating effect, always the refrigerant should be to the right of 4. So according to Ewing's model here, so the maximum COP is T0 by T2m minus T0, where T0 is the required temperature in the evaporator and T2m is nothing but at the discharge of the refrigerant, the discharge of the compressor. So that is T2m is the temperature and T0 is the evaporator temperature. So the same thing is given in terms of the wording here. So if at the suction of the compressor the state is 1 m and which is in the two-phase region, so that is in the wet state, and some others in the superheated region, even it may be beyond 1s also. Okay. So beyond 1s also, even the suction will take place to the compressor, but that will increase the more work input to the compressor. Then let us see the effect of various parameters on the coefficient of performance of the vapor compression cycle. So already we have seen coefficient of performance of vapor compression cycle is, so the refrigerating effect produced by the work input. So that is H1 minus H4 by H2 minus H1. Okay. So we can increase the COP. So COP can be increased. So when the suction pressure or suction temperature is increased, or the discharge pressure or discharge temperature is decreased. Okay. So there are number of parameters we can change it, or we can increase the COP. So one method here is decrease in the evaporator pressure. Okay. So if the discharge pressure, so or the evaporator pressure is nothing but the suction pressure to the compressor. So if it is decreased, then what will happen on the COP? Okay. So if the discharge pressure, so that is the discharge pressure of the evaporator. Okay. Evaporator pressure is nothing but the lower pressure. So condenser pressure is the maximum pressure in the cycle. If the minimum pressure is decreased, then what is the effect of COP? So if 4.1 is the actual refrigerating effect process or the evaporation process. 4.1 previous. So 1, 2, 3, 4. 4.1 is the actual evaporation. Okay. So if that pressure is decreased to 4 dash 1 dash. Okay, actual process is 4-1, but that pressure is decreased to 4 dash 1 dash. Then what is the effect on COP? So when the process is 4-1 here, getting effect produced is H1 minus H4. That is the area under 4-1. Okay. So with the decrease in the suction pressure or the evaporator pressure, the refrigerating effect produced is decreased. Okay. So it is only H1 dash minus H4 dash only. So the refrigerating effect is decreased. Then what is the work input? What about the work input? In the previous cycle, the work input is H2 minus H1. Okay. So whereas in this, with the decrease in the evaporator pressure, the work input is increased here. So that is H2 dash minus H1. So with this, the net effect is that COP decreases because the numerator decreases and the denominator increases. So the effect of COP decreases. So when the evaporator pressure is decreased, then always COP decreases. Then similarly, let us see. So when the discharge pressure of the compressor or otherwise condenser pressure is increased. Okay. So the actual cycle is 1, 2, 3, 4. And here the condenser pressure is increased to P naught dash. Instead of P naught, it is P naught dash. Okay. So the new cycle here is 1, 2 dash, 3 dash, 4 dash. So 1, 2 dash, 3 dash, 4 dash, 1. So that is the new cycle. So what is the effect on the refrigerating effect? So the refrigerating effect for the previous cycle is H1 minus H4. Okay. So for this cycle, it is H1 minus H4 dash. So the refrigerating effect is reduced. Okay, reduced by the area under 4 dash. Okay. So whereas the work input, also increases or decreases. So the work input also increases. Okay. So because here instead of H2 minus H1, now the work required for the compressor to operate here is H2 dash minus H1. With the net effect, COP also decreases. Okay. So when the discharge pressure increases, COP decreases. When the evaporator pressure decreases, then also COP decreases. Okay. So the reverse we can say. So in terms of temperature also we can say. When the evaporator temperature is decreased, then also COP decreases. When the discharge temperature or the condenser temperature decreases, then also COP decreases. Okay. So the same two parameters we can write for remaining two temperatures also we can consider. So condenser temperature and the evaporator temperature. So the same diagram here drawn for condenser temperature versus the refrigerating capacity. Okay. So when the condenser temperature increases, okay. So previously what we have discussed is in terms of pressure. Okay. So in diagram, pressure is again proportional to temperature. So if the condenser temperature increases, then the refrigerating capacity decreases and also the coefficient of performance also decreases. So the same is the case with the condenser pressure also. When the condenser pressure increases, then also the COP decreases. Then you can see the right figure also. So that is the evaporator temperature versus COP. So when the evaporator temperature decreases or evaporator pressure decreases, then also condenser this COP also decreases. Okay. Evaporator temperature means instead of 0 degrees centigrade, we are reducing to minus 10 degrees centigrade or minus 20 degrees centigrade. in that case also we have to require more work input also. So which will reduce the coefficient of performance. And this is the diagram showing the effect of condenser water temperature on the power. Okay. So here that minus 10, minus 20, minus 30, these are the evaporated temperature required. Okay. So this is the diagram versus the inlet water temperature in the condenser versus the power or the work input per ton of the refrigeration. So here when the evaporated temperature required is less, okay, minus 40 degrees centigrade, then so always we require more work input. Okay. So when the condenser temperature also increases, then also we have to increase more work input as compressor. Okay. So this is the diagram showing all the three variables. So evaporated temperature, inlet temperature of the condenser, and the power required for the compressor. Okay. So here when the evaporated temperature decreases, always work input will be increased. Then similarly, if the condenser temperature increases, more amount of condensed water we have to send out. Okay. With that effect also, the work input to the compressor also increases. So those are the four variables we have considered, the two pressures and two temperatures, so which will change the COP. Okay. Then let us see the improvement method. How to improve the COP. Okay. So COP can be improved or increased if the refrigerating effect is increased or the work input is decreased. Okay. So one method of increasing COP is superheating. Okay. So superheating is nothing but here at the suction of the compressor, if the refrigerant is in the superheated state. Okay. So that is dry compression. Then in that case the refrigerating effect produced will be more. Okay. So when the point at 1 is to the right of 4, what we have seen. So if it is beyond the vapor line, then more refrigerating effect will be produced. So that is the concept of superheating. So if the superheating is there, then the work required for the compressor to superheat to the discharge temperature. So that will also be more. Okay. So refrigerating effect is also more, and also work input is also more. If the increase in the refrigerating effect is more than in the work input, then we can get more COP. Is it not? So COP increases means, so numerator, so that is the refrigerating effect should be increased and the denominator should be decreased or maybe constant. But in this case with superheating, what is done here is refrigerating effect is also increasing and also the work input is also increasing. Okay. If the increase in the numerator is more than the increase in the denominator, then only we can get more COP. Okay. So superheating is always preferred only when the increase in the refrigerating effect is more than the increase in the work input. Otherwise, COP decreases. So you know what is superheating. So in which the temperature of the refrigerant is increased above the evaporating temperature. So you can see the diagram here. So with superheating. So the actual cycle here is 1, 2, 3, 4. So 1 is in the dry and saturated state. So 1 to 2 is compression. So 2 will be obviously in the superheated state. Then 2 to 3 is the heat rejection in the condenser, and 3, 4 expansion in the expansion valve, and 4, 1 is the refrigerating effect produced in the evaporator. Okay. So with superheating, instead of 1, it is going to 1 dash. Okay. So that is at the suction here, that point marked is nothing but 1 dash. So 1 dash 2 is the actual compression process. The whole compression is in the superheated state only. So it is an example for dry compression. Okay. So wet compression means compression should be within this wet region. So beyond that, so it is always in the superheated condition means, so it is dry compression. So with this, what is the effect on the refrigerating effect? So actual refrigerating effect here is H1 minus H4 only. With this modified cycle, the refrigerating effect is H1 dash minus H4. Okay. So the point represents here 1 dash. So H1 dash minus H4. The area under that represents the refrigerating effect. So the refrigerating effect is increased by the area under 1 dash. Okay. So numerator is increased by that much. Then what about the denominator? So denominator is also increased. Okay. So because here complete superheating state is there in further compression. So from 1 dash to 2 dash. Okay. So the area increase in the work input is nothing but 1, 2 dash, 2, 1. So that area represents the increase in the work input. Okay. So if the increase in the refrigerating effect is more than the increase in the work input, then we can increase the COP. Otherwise, COP will always reduce. So according to this diagram, so COP increases because the area under 1 dash is more compared with the area under 2 dash and 1 dash. Okay. So superheating increases both the refrigeration effect as well as the work input to the compressor. So superheating increases the specific volume at the inlet of the compressor, thus increases the work input. Okay. So when the refrigerant is in superheated condition, then the size of the compressor required will also be more, okay, compared with that of the wet compression. Hence the COP may or may not increase with superheat depending mainly upon the working fluid or the rise in the refrigerating effect or the rise in the working fluid. So the same thing given in terms of the pH chart, the pressure enthalpy chart here. So 1, 2, 3, 4. So that is the actual vapor compression refrigeration cycle. So with the superheating, the modified cycle is 1 dash, 2 dash, 3, 4. 1 dash, 2 dash, 3, 4. So with this, again we have to find out what is the refrigerating effect, increase in the refrigerating effect and increase in the work input. So if the increase in the refrigerating effect is more than the increase in the work input, then the COP will be increased. So superheating is one method of increasing the coefficient of performance of the vapor compression cycle, provided the refrigerating effect be more compared with the work input. So the same thing written in terms of the increase in the work input, the increase in the refrigerating effect. So here the actual COP is H1 dash minus H4 by H2 dash minus H2. So with the modified cycle, the increase in the refrigerating effect is H2 H1 dash minus H1. And similarly, the work input is also increases. Okay. So if the numerator is more compared with the denominator increase, then COP increases. Then another method of increasing the COP is subcooling of the refrigerant. So at the end of the condensation, the refrigerant coming from the condenser will be saturated liquid state. Okay. So that is our point 3. So 3 will be always on the liquid line. So when 3, so that is on the liquid line, is still decrease it to some other temperature lower than the saturated liquid temperature, then that will be called as the subcooling of the refrigerant. Okay. So subcooling means at the end of the condensation, the temperature of the liquid refrigerant will be lower than that of the saturated liquid temperature. So process of cooling the refrigerant below the condensing temperature for a given pressure. So that condensing temperature is nothing but the saturated liquid temperature. So this is done by using a subcooler or by using a heat exchanger. So subcooling increases the refrigerating effect producing and red. So for the same work input. So with this diagram you can see subcooling. So actual 1 to 2 is compression, then 2 to 3 is actual heat rejection in the condenser. Okay. So when the point 3 is, that point 3 represents that. So that is the condenser temperature. So where 3 is in the liquid state, that is the saturated liquid state. So when 3 is reduced to 3 dash, okay. So 3 dash, it is in the condenser itself, the heat is rejected to the condenser such that the refrigerant comes at 3 dash. That temperature is still lower than the actual condenser temperature, that is T3. In that case, it is called as subcooling of the refrigerant. Okay, and the refrigerant is cooled lower to the saturation temperature. So that saturation temperature is nothing but the condenser temperature. If it is cooled to lower than the saturation temperature, so by using some heat exchanger or by using some cooler, the refrigerant can be cooled. Then that is called as the subcooling of the refrigerant. So with subcooling, the modified cycle is nothing but 1, 2, 3, 3 dash, 4 dash 1. So it is 1, 2, 3. Again it is subcooled to 3 dash. Then 4 dash to 1. So that is the modified cycle representing the subcooling of the refrigerant. So with this, what is the effect on the refrigerating effect? So that is the numerator for the COP. Okay. So here using this, so if 3-4 is the actual compression process, so in the modified cycle, the actual expansion process, the actual expansion process is 3 dash 4 dash. Okay. So with this, the refrigerating effect is increased. So how much it is increased? So previously it is coming at 4, but here now it is coming at 4 dash. So because the refrigerant is still at lower temperature, so it can take more heat from the space to be cooled or the space to be refrigerated. So with this, the effect on the refrigerating effect, so that is, it is H1 minus H4 dash instead of H1 minus H4. Okay. So refrigerating effect is increased by the area under 4 dash. Okay, that hatched line. Then what is the effect on the work input? So work input is, so it's not changed. Work input is same, but the refrigerating effect is increased. So with that we can increase the COP. Okay. So by subcooling we can increase the COP always. But by superheating we cannot say whether it is increased or decreased. So the same thing we have drawn in pH chart and also even TS diagram. So previous cycle is 1, 2, 3, 4 with the modified subcooling here. The modified cycle is 1, 2, 3 dash 4 dash 1. So with this here we can increase the refrigerating effect. So the same thing again given in terms of the body. So without subcooling, throttling loss is equal to the hatched area under that B4-4C. With subcooling, throttling loss is given by the area A4-4-B. Hence, refrigerating effect is increased by the area under. So area between under 4 dash. Okay. So instead of H1 minus H4, now it is H1 minus H4 dash. Then why vapor compression refrigeration is preferred compared with the air refrigeration or vapor absorption system? So because it is having number of advantages. Okay. So let us see what are the various advantages of vapor refrigeration system. So COP is quite high. So as the working of the cycle is very nearer to that of the reversed Carnot cycle. So we have already seen that COP of the refrigeration vapor compression refrigeration is more. Why? Because the refrigerant is changing its state. So it can be converted from liquid to vapor or from vapor to liquid. So like that we can increase the refrigerating effect. Okay. So when used on ground level, the running cost of vapor compression refrigeration system is only 1/5 of the air refrigeration system. So last class we have air refrigeration system, okay, which are used for aircraft. Okay, so in that we have seen the advantage of aircraft refrigeration is that so at high altitude because compressed air is already available, we can make use of that. But here in vapor compression system, because this is used only on the ground level, so the running cost is only 1/5 of that of the air refrigeration system. So that's why these are mainly used for even low tonnage and also for high tonnage also. So for the same refrigeration effect, the size of the evaporator is small. So that is the main advantage of vapor compression refrigeration system. Okay. We can get any temperature required in the evaporator just by adjusting the throttle valve. Okay, that is not the case with the air refrigeration system. And coming to the disadvantages, so the initial cost is very high. Okay. And the other disadvantages are depending upon the type of the refrigerant we have selected. Okay. So if the refrigerant is toxic, then always toxic problem will be there. If at all some leakage of the refrigerant is there, then also it will be harmful. And also some refrigerants are very harmful also. Okay. And also these are inflammable also. So that's why. So the number of disadvantages compared with the advantages are less. So that's why vapor compression refrigeration is still used. Okay. So even eco-friendly refrigerants are there, so which are not harmful to the environment or to the human being. So those are preferred compared with the refrigerants used nowadays, freons and all this. So those are to be modified. Then whatever the cycle we have seen till now is the ideal cycle. So in the ideal cycle, what are the assumptions we have considered is compression is isentropic, then heat rejection is so at constant pressure, and similarly, so throttling is again isenthalpic, and also the heat abstraction in the evaporator. So that is also constant pressure, okay, and also constant temperature. But in the actual case, so number of deviations are there. So let us see the deviations. So those are the actual vapor compression cycle. What are the main deviations are that in the compression process? So compression is not isentropic. Okay. So that may be always polytropic. So we have to consider the efficiency. So that is the isentropic efficiency of the compressor to know the actual discharge temperature. So the refrigerant temperature in the evaporator is always less than Tc. So whatever the refrigerant coming will be always less than the required temperature that is to be maintained in the evaporator, that is Tc. Then the refrigerant temperature in the condenser will be always greater than Th. Okay, because that is due to polytropic compression in the compressor. And irreversible heat transfers have a negative effect on the performance. Next. Then so with this all these modifications, the net effect is that the decrease in the COP. Okay. So temperature of the refrigerant passing through the evaporator is reduced relative to the required temperature, that is the Tc. Then temperature of the refrigerant passing through the condenser is always increased relative to the temperature required, that is Th. So due to polytropic compression, always there is increase in the specific entropy. So instead of S constant here, S increases from 1 to 2. So that's why here, so isentropic efficiency, that parameter plays a vital role for the compressor discharge temperature. So the process is actually 4-1. So 4-1, the refrigerating capacity is same for the two cycles. So 1, 2, 3, 4, 1 and 1, 2s. So even though the compression is polytropic, but the refrigerating effect is constant. Okay, there is no change in the refrigerating effect, but the work input will be more. So with that, because the refrigerating effect is same and the work input increases, COP again decreases. So this is about the isentropic efficiency of the compressor. So you know this one. So the isentropic efficiency of the compressor is nothing but the actual work required to. This is not. So that is the ratio of the isentropic work. That is the minimum one. 1 2s by 1 to 2. Okay, that is the actual work required. So 1 2s is the isentropic work. So that you can directly find if you know the temperature at 1 and the 2 pressure. Okay, and also you can find out the discharge temperature from the compressor, that is 2. Okay, if you know the isentropic efficiency of the compressor. So that is H2S minus H1 is the isentropic work required. So whereas H2 minus H1 is the actual work required. So with that you can find out the actual discharge temperature. So that is T2. Then from this diagram you can see the actual deviations compared with the previous one. So why? Because here is it clear, this picture? So here so 1D is there, 1C, 1D, 1A, then comes 2, okay, then 2 to 2B, then 2A, 2C, and again 3, 3B, 3A. Okay. So here at the suction of the compressor, so at the suction of the compressor, always the refrigerant will be in the superheated condition. Okay. So why it is coming in superheated condition means here. So there is, so you can see starting from 4-1D. 4-1D is nothing but there is some pressure drop while taking the refrigerating effect or the cooling effect required in the evaporator. Okay. So pressure is also not constant during the heat abstraction. Okay. And similarly, at the suction of the compressor, this is in the superheated condition. So that is 1D to 1C. So 1D to 1C is nothing but superheating of vapor in the evaporator. So in the evaporator, actually more, because taking off more heat from the evaporator makes the refrigerant at the suction of the compressor in superheated condition. Okay. So that process is given as 1D to 1C. Okay. Then from 1D to 1C. Then 1C to 1D. Okay. So that is again superheating due to the heat available in the suction line of the compressor. Okay. So at the suction line of the compressor, because already it is in heated condition, so some heat is taken away by the refrigerant and again the superheat of the refrigerant will again increase. Okay. Then similarly 1B to 1A. So due to 1B to 1A is nothing but it is still in superheated condition, but some pressure drop takes place. So that pressure drop takes place due to the valve. Okay. So 1B to 1A is suction line pressure drop. Then 1A to 1. Okay, 1A to 1 is again, that is nothing but here again pressure drop across the suction valve. Okay, so that suction valve will open only when the pressure at the inlet of the compressor is still lower than the actual pressure. Okay, so that 1A to 1 is nothing but the pressure drop across the suction line. Similarly, the discharge valve will open only when the pressure of the refrigerant is greater than the discharge valve. Okay, so that is due to this one. Okay, so 1A to 1 is nothing but the pressure drop across the suction valve. So at the point 1 here, actual compression takes place. Okay, the refrigerant is compressed in the compressor, so it will come to 2. Okay, so 1 to 2 is, it is not isentropic, but it will be polytropic compression only. Then again from 2 to 2A, again there is pressure drop takes place due to the discharge valve. Okay, so that is 2 to 2A is nothing but the pressure drop across the discharge valve. And again from 2A to 2B, so again there is pressure drop takes place in the discharge line. Okay, then again from 2B to 2B to 2C. Okay, again from 2B to 2C, so that is nothing but de-superheating of the vapor in the delivery line or the discharge pipeline. So at the point here 2B to 2C, then okay. So de-superheating of the vapor in the delivery line is the 2B to 2C. Then at that point here 2B, it goes into the condenser. So where here, so from 2C, it goes into the condenser where a part of the heat is rejected, that is the de-superheating of the refrigerant, and again from that latent heat rejection also takes place to 3. Okay, so 2B to 3. So again in the condensation process also some pressure drop takes place, just like in the evaporator process. So with that, at the discharge of the condenser, some pressure drop takes place in the condenser also. Then again, subcooling of the refrigerant takes place from 3 to 3A. So 3A is at the bottom. Okay. Then, so because due to some liquid line here, some heat gain will take place. So that's why it goes at to 3A. Okay, the middle point is nothing but 3B. So that 3B, the temperature will be increased here due to the heat gain in the liquid line. So at the point 3B, actual expansion takes place in the expansion valve to 4. Okay, so 3B to 4 is the actual expansion in the expansion valve. So which is assumed as isenthalpic. So the same thing given in the pH chart also. So due to number of losses, pressure losses will be there, and also heat gain in the suction will be there, and also de-superheating in the discharge valve will be there. So with all this, the modified cycle changes in this form. So superheating, then subcooling is also there, pressure drop in the evaporator, pressure drop in the condenser. So with all this, the COP will be less compared to the ideal cycle. Then take this problem. This is a very simple problem on vapor compression cycle. So you can do the problems using the tables and even using the chart also. So pH chart is available. With that also you can note down all the enthalpies required. If you know the enthalpy at suction of the compressor, at the discharge of the compressor, and at the end of the condenser, then you can find out COP or the refrigerating effect or the work input, whatever it is required. So first thing is you have to find out the enthalpies at all the 3 points. The refrigerant 134A. So in the refrigerant nomenclature, we will see afterwards what is 134 stands and what is the chemical name of the refrigerant and all this. 134A is the working fluid in an ideal compression refrigeration cycle. The refrigerant leaves the evaporator at minus 20 degrees centigrade and has a condenser pressure of 0.9 megapascal. The mass flow rate is given as 3 kg per minute. Find the COP of the vapor compression cycle, then reverse Carnot cycle for the same maximum T max and T minimum and the tonnage of refrigeration. So at the suction of the compressor, the temperature given is minus 20 degrees centigrade. So nothing is mentioned at the suction of the compressor. Is it in that state or dry state? So you can assume that at the suction of the compressor, the refrigerant is dry and saturated condition. So T1 is minus 20 degrees centigrade and the pressure is given. So that is 900 kilopascal is given. So at state 1, so from the chart here or otherwise from the table for the refrigerant 134A. So note down the enthalpy at 1. So that is when the refrigerant is dry and saturated. At minus 20 degrees centigrade, the enthalpy of the refrigerant is 138.41 kilojoules per kg. And similarly, note down the entropy at 1. So from the same table for 134A. So at minus 20 degrees centigrade, note down the entropy of the vapor refrigerant. So that is Sg. So Sg is nothing but here S1, which is 0.9456 kilojoules per kg Kelvin. And similarly at the state 2, that is at the pressure of 900 kilopascal, from the pressure tables at 900 kilopascal. So already these values are given. Okay. So at that discharge condition, the entropy is given as 0.9456 kilojoules per kg Kelvin. And similarly, the enthalpy at discharge also given. So 278.23 kilojoules per kg. And the temperature is also given. So that is 43.79. Then 3 is nothing but after condensation. So here it is coming as saturated liquid. So at 900 kilopascal here, so it is in the liquid state. So dryness fraction is 0. So the enthalpy given at that exit condition from the condenser is 101.61 kilojoules per kg, and the entropy is also given as 0.3738 kilojoules per kg Kelvin. So at state 4, 3-4 is nothing but isenthalpic process. So enthalpy at 4 is same as enthalpy at 3. So that is the enthalpy is given as 101.61. So at the end of throttling or expansion, it is again 101.61 kilojoules per kg. So with all this, we can find out COP of the vapor compression refrigeration cycle. So that you can find out by finding the refrigerating effect. So refrigerating effect is nothing but M into H1 minus H4. So So H1 value is known, H4 is also known, and that M is same in the numerator and denominator. So you need not consider that value M. And similarly the work input is H2S minus H1. Okay. So all those values are given. So COP of the vapor compression refrigeration cycle is 3.44. So that then you can find out in terms of refrigeration, you can find out the cooling effect. So that is M into H1 minus H4 is the refrigerating effect produced. So that is M is given in 3 kg per minute. So you convert that to kg per second. So 3 by 60 into H1 minus H4. So if you divide that by 3.52, you will get in tons of refrigeration. Or otherwise here it is given in kg per minute. So that's why, so 1 ton of refrigeration is equal to 210 or 211 kilojoules per minute. So you can divide with 211 also. Or otherwise you convert M into kg per second, or as it is you keep in kg per minute and divide by 211. Then you will get this in tons of refrigeration, which is equal to 1.94 tons. So again you can find out COP of the reversed Carnot cycle. So that is the lower temperature by the maximum temperature in the condenser minus the evaporator temperature. So condenser temperature is already given 43.79. So with that you can find out the COP of the reversed Carnot cycle. So that is 3.97. So that is all. That should be always greater than that of the COP of the vapor compression cycle. So which is here 3.44. Okay. Then take another problem. And also the work required. So work input is also asked in this question here. So you can also find out the work input is nothing but again the mass of the refrigerant into the work input to the compressor, H2 minus H1. So like that also you can find out. So but here it is asked in terms of horsepower. Okay. So that horsepower conversion is known. So 1 unit conversion is 4.715 horsepower is equal to 1 ton of refrigeration. So you can divide that, you can find out that in HP per ton. You note down this problem. So this is on the actual vapor compression cycle with number of deviations. So the main deviation is the compression is polytropic. So the table provides steady state operating data for a vapor compression refrigeration cycle. Using the refrigerant 134A as the working fluid for the mass flow rate of 0.08 kg per second. Determine the compressor work or compressor power, refrigeration capacity in tons, COP, then isentropic efficiency of the compressor. So at all the 5 states, the enthalpies are given. So this is also a very simple problem. No need to find out anything. All the enthalpies are known. So at 1, that is at the suction of the compressor, the enthalpy is 241.35 kilojoules per kg. And at 2s, at 2s, that is assuming that compression has isentropy. So the enthalpy at 2s is 272.39 kilojoules per kg. And 2 is the actual discharge condition of the refrigerant. So that is the polytropic compression. So 2 is 280.15 kilojoules per kg. And 3 is the point after subcooling of the refrigerant in the condenser. So it is 91.49. And you know that 3,4 is isenthalpic expansion. So H4 is same as H3. So 91.49. So with all this, find out the compressor power. So that is H2 minus H1 into mass of the working fluid of the refrigerant. Okay. So that is Mr into H2 minus H1. Then refrigeration capacity. So that is again Mr into H1 minus H4. Okay. Then the coefficient of performance. So refrigerating effect by the working fluid. Then isentropic efficiency of the compressor. Isentropic efficiency is nothing but the actual work required. So that is H2S minus H1. That is the isentropic work by the actual work H2 minus H1. So that will give all these. So note down the answers also. M into H2 minus H1 is the work input. Then refrigeration capacity. So M into H1 minus H4. So the work input to the compressor is 3.1 kilowatt and the refrigeration capacity is tons of refrigeration. So that is M into H1 minus H4. So if M is in kg per minute divided by 11. Otherwise if M is in kg per second then divided by 3.5. Get this in tons of refrigeration. Then coefficient of performance. So H1 minus H4 is the refrigeration effect by the work input H2 minus H1. That is 3.86. Then isentropic efficiency of the compressor. Isentropic work required H2S minus H1 by the actual work required for compression H2 minus H2. So that is 80%. So the problems on vapor compression cycle will be on wet compression or dry compression. Okay. Or maybe at the suction of the compressor, maybe in superheated condition, or maybe subcooling also. Okay. So with all this, so number of problems can be done. So sometimes you have to find out the temperature at the discharge of the compressor. Okay. So if T1 is given and P1 is given, so P2 is also given. Then you have to find out what is the superheating temperature at the discharge of the compressor. Okay. So by equating the entropy, okay, entropy at 1 should be equal to entropy at 2. So entropy at 1 because that is dry and saturated, directly from the table we can note down S1. But what about S2? How to find S2? So that is the saturation temperature, okay, at the maximum pressure that you know. Okay. So that plus so Cp of the vapor into John T superheating temperature by T saturating. So with that you have to find out the superheating temperature at the discharge of the compressor. So after finding the superheating temperature at the discharge of the compressor, you have to find out the enthalpy at 2. So enthalpy at 2 you can find out. So how? So Hg value should be equated to the enthalpy from saturation to superheating temperature. So that is again Cp of vapor to T superheating minus T saturation. Okay. So in thermodynamics we have all studied. Is it not? So we'll see some problems on that also. Okay. How to find out the discharge temperature of the compressor. Okay. So how to find out the superheating temperature. So after you know the superheating temperature, you can find out the enthalpy very easily. So because enthalpy of the vapor at that temperature plus so whatever the heat added during superheating. So that is H2 minus to the saturation. If you take a point somewhere, some 2, okay, in between the vapor line, then that heat should be added. So that is Cp of vapor into T superheating minus T saturation. So selection of refrigerant plays a vital role in vapor compression refrigeration. So whether for performance, safety or for environment, so it should be selected such that environment is not affected and the safety precautions are taken, and also the COP is also should be high. See about the refrigerant after completion of the vapor compression. So last class I have given one simple problem on aircraft refrigeration. Have you done that? So what are the conditions given? What are the pressures given? Temperatures given? So first you note down those. Then find out the remaining temperatures. So with that you can find out all this. At what temperature does the air enter the turbine? So T5 is required here. So once T1 is given and the pressure at 2 is given, so you can find out T2. Again from T2 you have to find out T3 dash because that pressure will be given. Okay. From the isentropic efficiency here, so you have to find out T3. So after finding T3, then T4 is given. Then find out T5 dash. After finding T5 dash from the isentropic efficiency, again find out T. Okay. So after knowing all the temperatures, then only you can do the problem. How much power does the turbine supply to the fan? So whatever the work done by the fan in simple cooling system is used for driving this fan. Okay. So whatever the work done by the turbine itself, you have to find out that should be equated to the work required for the fan to operate. At least take the solution. So first again read the problem. What are the data given? What you have to find out? Turbine efficiency is given as 80%. So M is given as 7.5 kg per minute. And turbine pressure is given as 4.4 bar. And the cabin pressure is given as 1 bar. So cabin pressure is given as 1 bar. And the discharge temperature is minus 6 degrees. Turbine. So the method by which have to first find out all the required temperatures. So up to T5 you have to find out the temperature.
PPT. Sorry.
You already said. So this is the problem on simple cooling system. Then simple evaporator system. Then evaporator. So with all this, number of steps will be increases. Okay. So finding of all the temperatures. First thing is you have to find out all the temperatures. Then whatever the required you can find. So till now we have seen just the basics of vapor compression. So the next class will go in detail. What are the causes of superheating? What are the causes of cooling? How it can be achieved? Then what are the other methods by which COP can. Hello? So where now your doubt? Oh, any question? Any doubts from you?
Hello, I am ready college. Hello, please pose your question. Actually, madam waiting for. Hello.
Hello?
Madam,
Yes please.
no doubts, ma'am.
Any doubts from you? Are you taking the notes or something? So some problems will be on the capacity of the compressor, the size of the. So here also the size of the what is L by D diameter. So such type of questions will be asked in vapor compression.